The broadcast is now starting. All attendees are in listen-only mode.
All right, hello everyone. My name is Sara Brock. I am a program manager with the Groundwater Foundation. In the chat, could you guys just check in and make sure that you can all hear me, you can see my screen, just say hi, that kind of thing. We're going to wait just a couple of minutes while a few more people join us. Hello, everyone. Can everybody hear me? Can everybody see my screen or my face? Let me know in the chat. Still waiting for a couple of people. Not seeing anybody responding. Are you sure you guys can see me or hear me? Or you can raise your hands if that's an option. All right, I've got 2 people raising their hands. Hello, you can see me. All right. Well, if you have any questions or at any time you can't see me or hear me, just go ahead and, just go ahead and let me know in the chat. The chat box will be open on my screen as well, just to make sure that I receive your questions. So, perfect. Okay, awesome. So we're going to go ahead and get started. Thank you all for attending this webinar, this Recharging Groundwater Education webinar. My name is Sara Brock. I have been with the Groundwater Foundation for about 3 years now, 3.5 years now, 4 if you include the time that I was an intern before being hired on. I'm gonna turn off my webcam just for a little bit so we can focus on the screen so I can save bandwidth. Yeah, so like I said, my name is Sara Brock. I've been with the foundation for about 3 years, and this entire time I've been working with these tools, which many of them were developed prior to me coming on with the foundation. But since I've been brought on, I've been working a lot with teachers, getting these tools into classrooms, and just generally making sure that these educational tools can fit a variety of settings. So whether that's a formal classroom that has to adhere to certain science, state or national science standards, whether that's a camp, a summer camp that's just out there to have fun and stay cool on a hot day. You know, we really do our best to make sure that these tools are accessible and still educational and rigorous, and good for all ages. So I work for the Groundwater Foundation. Many of you have heard of us before, but if you have not, our mission is to connect people, businesses, and communities through local groundwater education and action, making us all part of the solution for clean, sustainable groundwater. So I work remotely from Lincoln, Nebraska, but our home office is based in Westerville, Ohio. We are under the umbrella of the National Groundwater Association, which is a professional association for groundwater science and well drillers and water well professionals. So we have a lot of, just little mini plug for NGWA. They have a lot of educational materials and resources for the lay person who is not, K through 12 or early college, for the people who maybe work with it or deal with it as a part of their livelihood. So that is kind of very briefly who we are and what we do. This presentation is directed towards educators, primarily classroom educators, K-12. I work a lot with the public education system, with the Lincoln Public Schools, the Omaha Public Schools here in Nebraska, and then I've worked with them throughout the state and throughout the country as well. So I see some of you who are attending, and I've worked with you before, possibly, and I know that you guys may be experts on groundwater, but what we want to do is we want to make sure that the teachers who are teaching, the educators, informal or formal, who are educating, are content experts, at least as far as their students need to know. So I like to review what groundwater is in the simplest and most human way to think about it, which is the water that we drink, the water that grows our food. It's important for industry, recreation, and wildlife, and it's the environmental bottom line. So thinking about groundwater, which is this abstract concept that we can't really see, as something that is very meaningful to us. So that's kind of my first line of attack is, all right, let's take this invisible resource and let's actually bring it to life. Let's make it meaningful. Many fifth graders, because here in Lincoln, our public school system tackles groundwater for the first time and the water cycle for the first time at fifth grade. Most fifth graders are able to tell you that 70% of the Earth's surface, or about 2/3, is covered in water. Maybe about half of them will be able to tell you that this water is available for human use. And it's the few and far in between. It's the real smarty pants who've studied ahead that can tell you that most of this usable water is stored beneath our feet as groundwater, that the rest of it's locked up in glaciers or ice caps or stuck in the atmosphere, or salt water, so totally unusable. And then this is for everybody, because too often it's easy to think about, why do we need to study this invisible resource when surface water is it's so easy. It's right there. My students can go wade out in the ponds or in the wetlands and gather samples. But because it is so important and so critical for many water systems, city, public, and rural water systems. Pressure is expected to increase with the growing population. Contaminated groundwater resources, everything from PFAS, which is an emerging contaminant that is from everything from like firefighters' foam on military bases to the nonstick covering of our nonstick pans. And it doesn't go away. It just keeps spreading, and just a tiny, tiny bit can hurt us. And we're just learning about it now is the crazy thing. So we've got quantity issues, we've got quality issues, and all of that water is stuff that we're expected to drink. So we're tackling this from an education perspective, making sure that the students know going into their adulthood where they make their decisions, they understand where their water comes from. They understand how water moves and travels beneath the surface. And hopefully they use that information in order to change those things and make the world a better and cleaner place for our water. So we like to tell the teachers who already know this, that today's youth are tomorrow's decision makers, scientists, teachers, innovators, environmental students, and leaders. So get them started from an early age, help them understand the basics. So moving specifically to what the Groundwater Foundation offers as a part of our Educator Toolkits, what do we actually give formal and informal educators to help them get their students to the next level, to help them establish that base? We have our awesome aquifer kits, which we will be demonstrating today, and the TAPS activities. I'm going to get into that a little bit later, so I'm just going to skip over that here. We have a searchable activities library that you can search for lessons, you can search for games, you can search by duration of time that you want to do that thing. You can search by topic, whether you want to tackle something like irrigation or if you want to talk about water quality, or if you just want like a coloring page or a crossword. Teachers need 5 minutes break here and there, so we offer them that as well. We have a couple of screens on tools. We've got 2 mobile applications, something called 30 by 30, which is a water use tracking app available on Apple and Android. So you enter the amount of water you use each day, and the goal is to reduce your consumption by 30 gallons over the course of 30 days. And then we have a trivia app, which is really fun. We just spent a year kind of redoing it. We've got all kinds of levels. I'm not going to go into this too much later on. So if you have questions about it, I'll answer that at the end, but I wanted to take a little time here. This is kind of like Jeopardy for students. If you need a fun review game, or you want to challenge students in their water trivia questions, their water knowledge, you can use that. And then Brains On, we will be demonstrating the Hydrogeology Challenge today, so I'm not going to talk about that until I get to it. The Hydrogeology Challenge can be teacher guided or it can be student driven. And then we have some learn at home lessons. When the pandemic hit, we were in the process of using a grant to reduce some of our get out in the public materials. And obviously that was not going to be useful for anybody. So we pivoted and designed some learn at home lessons. We've got currently 4 lessons on there. I think water quantity, aquifers, groundwater basics, and possibly the hydrologic cycle. I'm a little fuzzy on which 4 are up there, but they're based off of the categories in the Water Wonder trivia. And there's, again, coloring pages, some fun lessons and activities, and little quizzes. So something teachers or homeschool co-ops can use, or a camp counselor if it's a rainy day and they just need a filler. That some of those can be student driven as well, and then some of them are a little bit more complex and might ask for an older sibling or older adult to mentor them through the lesson. But I won't be talking about too much about that later on. I will just be focusing today primarily on the Hydrogeology Challenge and the Awesome Kit. All right. So I'm going to open up my screen here again. All right. So hopefully everybody can see me, because I will be doing the demonstration via this way. Our Awesome Aquifer kits are kind of our pride and joy. They are a 3-dimensional water modeling kit that literally brings groundwater into the classroom. So again, like I said, one of the chief difficulties of understanding groundwater is the fact that we can't see it. So we have a nifty little box here that you can kind of see in the corner. I'm going to stop sharing my screen here for just a minute so that you can see my webcam. I'm going to move it away from my lovely face so you can see the even lovelier Awesome Aquifer kit box. So this comes as a kit with almost everything you need it to do 6 activities. Got a lid, which is actually quite important because it helps you clean out the kit. We've got the instruction manual, which has a glossary and then several activities. The 3 we will be doing today are groundwater and surface water interaction, pumping the supply, and contamination clues. But there are others, and I will review them at the end of the demonstration. We've got a syringe. Got 2 pieces of plastic tubing and a little lotion pump. Comes with some food dye and some modeling clay. Got a little baggie of activated charcoal, which you can't see against my black shirt, but that's okay. There we go. Got some sand. And gravel. This is standard fish gravel. Coffee filter. A piece of nylon. A couple rubber bands. And some of these little medicine cups that are about 30 milliliters or 2 ounces, roughly. So all of these things are useful. And I will say, we do sell the Awesome Aquifer kit, like that's one of our products. But most of these things, top secret, but most of these things you can purchase from, a pet supply store, Home Depot, or Menards, or, some local hardware store. You can find those most places. What you can't find, put this back in here, is this box. This box is actually quite tricky to find, and it is probably one of the more useful tools because just in terms of cleaning, sometimes there's a little hole punctured at the top. This one does not have that. But when you pour the gravel out, it cleans and drains the kit very easily. So, you can run around, go to 5 different stores and purchase the kit's activity, purchase the necessary supplies if you like, or we just kind of sell it in one neat little box. Right. I'll stop here just for a second, make sure I've answered. Nobody has any questions yet. Okay. All right, we're gonna move on to the actual demonstration. So I'm gonna quick share my screen one last time. So like I said, today we'll be doing the groundwater, surface water connection, pumping the supply, and contamination clues. During this demonstration, I want you to turn on your teacher brains. Now, usually I would do this with you guys, and I am so bummed that I cannot have you play in the gravel with me, but we're going to make this work. So with your teacher brains, trying to think about what kind of interdisciplinary connections can you make to math, to science, to history, to English. What other disciplines can we work with? How can you possibly extend this activity? I will say that in the instruction manual, we do offer some options to extend the activity, but it's up to you. We want you to be creative with it. And then also, what might be especially difficult what might be especially difficult about these concepts, and how can you enhance or clarify these activities so that your students can understand them if they're struggling? All right. Turn my screen back off so I can focus on this. But the first one we will be talking about is our groundwater surface water connection. Now, I do these demonstrations a lot, like a lot. So I'm going to be using a demo box here. That is a little old, a little ratty, serves me well. I've got the same things. If your kit's brand new, you can have students pour the gravel in. Otherwise, I tend to just leave the gravel in there once I clean it out after each section. But we start off by talking about, what is a model? A model is something that scientists use to help us understand the world, especially things that we can't see and relationships that are harder to define. So we talk about what this represents. Well, this gravel represents the Earth. This box here represents some kind of geological boundary. If we add water to it, I will say, cups not included in the osmographer kit. Bring your own cups. If we add water to it, we're going to track and see what happens. We're going to add water to just one corner, add it very slowly. And I've dyed this water blue to help us see things just a little better. I'm going to add about half the cup of water. Now notice I'm only pouring this into one corner. I didn't pour it anywhere else. And yet, the water moved, the water traveled. So with this osmographer kit, just by pouring a little bit of water into a box of rocks, we've now established a very important concept that nobody thinks about. We've established the fact that groundwater moves. Water travels through the subsurface. And we can get a little bit crazier, roll up our sleeves, and we can make a mountain. Students like this part. Now I have a little mountain. I didn't add any more water to it. I didn't do anything except for move some rocks around, but all of a sudden I've got something over here called surface water, which is pretty wacky. So now students are thinking about, so the height, the elevation of the land will help me determine whether I've got groundwater or if I've got surface water. And here I usually stop and I cover some pretty important vocabulary, things like the water table, the unsaturated zone, and then the saturated zone. Talk about where the aquifer is located. And then I let them pour some more water in. What happens if they pour water over the dry land? What happens to the surface water? What happens if I pour some water over surface water and make it rain, so to speak? The water table elevation increases if I add more water to it, no matter where I add water. So now we can talk about things like recharge. So we've demonstrated parts of the water cycle. We've covered some key vocabulary. We've established the fact that water moves. We have linked surface water and groundwater. just by pouring water into a box of rocks and moving it around a little bit. And that is our groundwater surface water connection. Just that one activity, and we've covered so much. Moving on to the next, pumping the supply. I'm going to give you guys just a second to look at the screen here, which I shared again for you. Let me know if you are having trouble seeing it. Perfect. So now we get to talk about pumping the supply. Now we get to talk about where our water actually comes from. I'm going to take away my screen and focus back on the demonstration. So pumping the supply, where do we get our water from? Our water that we use to drink, to bathe, to shower, to water our crops and water our animals. Well, we get it from a well. And again, models help us see things that we can't really see ourselves. So we're going to model a well, which is going to go into the subsurface and help us pick up some water. So we've got this piece of plastic tubing, which represents the well casing. So I like to tell students, what happens if you dig a hole in the earth and you don't put anything around it? If you try to bring up water, what's going to happen? Well, either the well might collapse, or we're going to get a whole bunch of gross dirt coming up with our water, or even worse, the water isn't going to come up. It's going to flow back into the ground. So we got that. I also like to say, okay, so what happens if we bring the water up and we don't have anything to filter out some of the big particles? Well, again, we're going to get some really, really gross stuff coming up with our water. So we use this piece of nylon as our well screen, and we attach it to one end of the well, the end that will be going into the bottom of our aquifer. And that's what those rubber bands are for, attaching our well screen. All right, so now we've got a well screen, we've got some well casing. We need one more thing, and that's to help us fight some gravity. We need a pump. This is what our syringe is for. I like to start out with a syringe, just because it's easy, it makes sense. We attach the syringe to the other end. And now we have our model well. One last thing we need to talk about before we actually get to pumping water out of our aquifer is something called well siting, or the location where we place the well. Now, students are going to be like, put the well in the lake, because that's where the water is. We don't want to do that. The metaphor or the analogy that I like to use is, if I have a cup of water here, and I spill some salt next to it, well, I can sweep up the salt, right? The salt can go away. I can take care of it. But what happens if I spill the salt into the water? Well, I can't drink it anymore. And since a well is a direct line into the groundwater below, that contaminated surface water is going to get into our groundwater, and our groundwater is a lot harder to clean than just dumping out a cup. So we like to put it into some land that is away from things that can easily contaminate it. And we like to make sure that our well screen is well below our saturated zone. So here's where we use that fancy word again, that saturated zone. And make sure my well is in. See if you guys can kind of see it. Kind of stuck in there. And then I pull some water up. This is the water that I am going to use to make spaghetti tonight, or to go swimming in, or so on and so forth. This tends to be their favorite part. I usually give them a solid minute or two to pump out some water. So as I'm pumping, maybe you guys heard that weird little squeal sound. It's getting harder for me to pump out water. Harder and harder. And our lake went down too. Our surface water elevation went down as well. So now we get to introduce the concept of depletion. We talked a little bit about recharge earlier, but now we get to talk about depletion. What happens if we take more out than we can put back in? And now here we've got several ways to do that. We can say, okay, make it recharge again, make it rain or sleet or snow over the land, over the lake. What happens if we put all the water in at once? It's a flood. Or we can talk about things like drought. Students, I've had several students who they've kind of shocked me with how intuitive they were. They say, all right, Sarah, what happens? I'm going to pump out a little bit of water here just a sec. What happens if I fill up my syringe again and build a well and push the water back in? And so then I have the opportunity to talk about things like injection wells, which is just a really cool thing that you don't usually get to bring up. So we've talked about one kind of well, which this is pretty easy to use. I can pull it up. I can get a lot of water pretty quickly. So we talk about this syringe as a high capacity well. So things like industry or agriculture, they might use this. But we do have another option here, this little lotion pump. So we attach the lotion pump. We dig a well, not in the middle of the lake, Sarah. I've got to be better than my students. All right, so dig a well. I'm going to move this up a little closer, back this up so you guys can see. All right, now I get to actually use some pumping action. It's taking me a lot longer to get the same amount of water and a lot more effort. My thumb's getting pretty tired. So this is what we would call a low capacity well. This would be like a domestic well, something that a farmer might use to make sure that he and his family have enough water for their household, but maybe not their livestock. Or if they had just a small farm, maybe their livestock. Got some water here. Yeah, always make sure you guys have some paper towels or something to clean that up with. I forgot. It's fine. But so now I've got to talk about things like low capacity, high capacity, domestic, and industrial, agricultural, all with just these few things. All right, I'm going to switch back to my agricultural well really quickly. I'm going to share my screen one last time before the final demonstration of the Asimov core kit. Oh, right. So just to recap, we've talked about the model of a well, we've talked about well siting, we've talked about the effects of pumping, depletion, and recharge. Here is actually a really nice place where you can identify the limits of models. So for example, this is a small model, therefore we can't necessarily see things like cone of depression or area of influence. We don't have that ability because of the size and the scale of the model. So I know next generation science standards, which I'm just going to refer to as NGSS from here on, NGSS is really leaning into the modeling. They really like students to experience the models and the limitations and comparing and contrasting different mechanisms. So here's an area where you can really identify that. Then our final demonstration will be contamination clues. So we get to talk a little bit about contaminants. We can introduce a very simple one. We can look at locality, we can identify plumes, and we can really look at human impact. Again, NGSS has a really intense focus on how humans are impacting the environment around us. So this is a really nice opportunity to look at that in a very straightforward A to B relationship kind of way. So I'm gonna, where'd my mouse go? There. Okay, so I like to use a little story with this. I like to say that there is a river that runs in between two farms. And Farmer Johnson lives on one side of the river, and Farmer Brown lives on the other. And Farmer Johnson on the side of the river, he is in accordance with all of state and local recommendations. He is voluntarily putting in monitors on his wells. He is keeping track of his nitrogen use. He is in application. He's keeping track of how often he irrigates and when he irrigates. He's following all of the local rules, and his plants are absorbing the fertilizer as they need it. Farmer Brown, he needs to rake in that money this year. He's maybe gone through a couple tough years, and he's like, all right, I'm just going to give my plants everything, all they got, more fertilizer, more crops, let's go. So he applies a lot of fertilizer, which is going to be represented by this kind of bluish purple coloring. So he's just going to apply all over. It rains and it doesn't all get absorbed. I'm just going to add maybe about a third of the cup. Well, already, I can hold it up to the light a little bit. Hopefully you can see that there is some plumes. There's some evidence of the purple within the groundwater and even within the surface water with as much as I added. Hopefully you can start to see that. Well, Farmer Johnson, I'm going to have this blue here to help us remember what our watercolor started out as. Farmer Johnson needs some water for his family and for his crops. So he's going to put in his well and start drawing up some water. I'm going to put it into this empty cup so we can see. This is water that he might be drinking. This is the water that he might be applying to his crops or giving to his cattle, or pigs, chickens. Pull up some water. All right, so we got some water going. It rains again. We got some purple water coming in on some contaminated runoff. We've got some nice clean water on Farmer Brown's side. I'm going to pump some more water. Now, I'm going to just stop here because you can probably see that my river is now entirely purple. And maybe you can see we've got some subsurface contamination throughout. Now, I never pumped on Farmer Brown's side, but can you see the difference in our contaminated water versus our clean water? Like, that's crazy. Now, it's not quite as bad as our obviously contaminated water, but still, it's not something we'd want to drink. So then you ask students, you say, all right, so what should Farmer Brown do? What should be done? What should Farmer Johnson do? And the usual response is we'll stop applying fertilizer. And that'd be great if we could grow the amount of crops that we needed to feed the whole world without applying any additional substances to help get that growth. But that's not the way the world works. Sometimes we need to make sure that sometimes our soil isn't perfectly healthy. Sometimes it's just a bad year. We need a little extra phosphorus or a little extra nitrogen. So we get to talk about that gray line. We start to get to talk about that gray area of what we do affects people downstream. So we need to be conscious of that. But there's not a clear right and wrong answer. There's guidelines we can follow. There are things we can do to remediate, to treat. And so here we get to introduce the concept of remediation. So what if I had started pumping out the purple water where I'd applied it? Well, then there would be less purple water, right? So talking about, pump and treat as a method. In the kits, you're also given clay. What happens if I make a clay barrier? We talk about physical barriers. And these are all things that you can actually do with the kits. Additionally, in the kit, there is that activated charcoal, which is a different activity called Clean It Up. That Clean It Up activity gets to talk about charcoal remediation and filtration. So there's another method, a more chemical method of treating groundwater. So there's that. And I always do this. I always run over time, so I'm very sorry. I'm going to move on a little bit. But before I do we have any questions about the osmographers demonstration? Okay, I'm going to go ahead and move on then. So osmographers in the classroom, student-driven learning and investigation. This can be done literally just by handing each group of students. It's best done between 2 to 4 students. You can just hand each group of students a box and say, go for it. That's a 3D model that I've used with adults as well. So if you guys are able to do it with any kind of educational event. I do have a question here from Becky saying I referred to it as digging a well instead of drilling. You're right, I do need to refer to it as drilling a well. I think there are still some dug wells, but it's not well-used technology. It's long and exhaustive, and yeah, just you're right. Drilling a well is the way that it is typically done. Thank you. Additional instructional videos for the osmoc kit are available at our YouTube channel, youtube.com/GWFDN. Just some cleanup hacks for teachers, because we know you guys don't have a whole lot of time in your time banks. The activated charcoal does need to be rinsed in order to get rid of that activated charcoal dust prior to. If you do not rinse the activated charcoal and you try to use it to filter the colored water, you're going to end up with some really gross water, and your students will be like, why didn't this work? So yeah, make sure you rinse that charcoal, speaking from experience. Use a spatula or some other, maybe plastic ID card or something to thoroughly remove the clay. That clay can get stuck onto the side of the kits and get really gross if you don't clean that thoroughly. There is a manual. If you do order several kits, kits are available for retail at $40 per kit. But if you do order several kits for your classroom or your organization, there's a manual on how to effectively clean and dry multiple kits that is available within the Educator Toolkit. And I'll throw those links up here at the end of the webinar. And then, yeah, make sure you thoroughly clean the kit at the end of every unit if you're using this as a part of the unit, or if it's some ongoing project, multi-week, multi-month project, every couple of weeks, just make sure you rinse the rocks off. They can get a little mildewy and start to smell funny. Other osmographers kit activities you can do. So I did talk briefly about the Clean It Up. Discover porosity and permeability. That is where that sand and those medicine cups come into play. So get to talking about how how much water can a substrate hold, how much water sand or gravel can hold, and if you want, you can even dig up some local dirt and compare that. And then also how quickly water can travel through those substances. We also have something called Teaching About Protecting the Source, which is our TAPS manual. And these are activities designed primarily for middle school to high school level. They are aligned to NGSS, and they focus primarily on human impacts. So things like improperly abandoned wells, sinkholes and erosion, which is not totally human impacts, but will impact humans. And then things like fertilizer, underground storage tanks, improper landfills, and improper fracking wells. So these are things, again, exploring that gray line between what is good and helpful for the economy, but also cognizant of the land and the water that we're going to live with for the rest of our life. So briefly going to run through this. Again, this will be available as a recorded session, both emailed to you, and it will be up on our YouTube channel within the following week. So NGSS alignment for the regular Awesome Aquifer Kit activities and for the TAPS extension activities. And then briefly, I want to run through the Hydrogeology Challenge. The Hydrogeology Challenge is designed for, really advanced middle school. Like if you have an insane middle school science team, go for it. But they do require a basic understanding of geometry and algebra in order to work through some of these concepts. So middle school is like the very, very bottom entry point, and then 9th through 12th grade primarily. So it's just a fun computer model that allows them to see how water travels and allows them to calculate it through triangulation. So you got some vectoring in there, and some slopes and velocity. So I'm going to quickly demonstrate this. Oh, thank you for holding that for me. So we have two versions of the Hydrogeology Challenge. We have the public front-facing version, which is groundwater.behere.net, or just Google Hydrogeology Challenge, and we are the first thing under Google that pops up. So you can just hit start the challenge. You do have an option to choose between several maps. I'm going to stick with this one. You can choose your wells. And then we can work through, calculating the direction of flow, calculating the gradient or the slope of flow, and then calculating the horizontal velocity. The horizontal velocity is very important because we're talking about direction, not just speed. In this, we get to identify things like the ground elevation, which is G here, our water table elevation under static or non-pumping conditions, and our water table elevation under pumping conditions. So remember, again, we weren't able to see that cone of depression. We weren't able to see the effect of pumping in the Awesome Aquifer Kit, but here we can see at least a numerical representation of what happens when we turn a pump on at a particular location. We also get to have fun with a little bit of a well log, very basic version of a well log. So we get to talk about geology. What is the substance underneath the earth? What is its K, its hydraulic conductivity? So how easily it can pass through a substance. Or its porosity, how much water can be held in that substance. We get to talk about the depths, how the geology is layered over time. You turn the pumping on, then this model self-calculates using the appropriate pumping conditions. If this pumping is turned off, then you can use static conditions, and you just work your way through answering the questions. It's pretty self-explanatory. With the public-facing version, you do get a check answer button. So clearly I got everything wrong here. And if I just can't get it, I get to click the Show Solution button, which will help me figure out where I went wrong. What was I reading wrong? And maybe my pumping was turned on, but I was using the static water table elevation. And so I get to work through that. Then we have our reality checks. Our reality checks are especially cool in the public-facing version because here again, we get to talk about the limitations of modeling and what is the model showing versus what we are showing. And we have that for all three, for flow direction, for gradient, and for horizontal velocity. Now, the testing version is something that we offer exclusively to educators for free. We offer 3 versions: the Hydrogeology Challenge, HGC, beginning, middle, and in high levels. So that is based on the number of wells that are available. This has, I think, 10 wells in it. The beginning has 5, and the middle has 6. So that, I'll talk a little bit about the importance of that in a second. But I'm just going to click 3 wells here. And again, you walk through the same procedure. You still get your well log. You can still choose pumping on or off. But here, there is no check answer or show solution button. There's also no reality check feature. The students are expected at this point, if they're going through this, to understand what this model is showing and what this model is asking of students. When they get to the end of this, they can submit, and educators also get an exclusive test results location. So this is one that I did from professional development back in 2017, again with a lot of local teachers, Lincoln and Omaha teachers. And we had them work in groups of 2 to work through. And then they submitted to a location. They submitted with their first names and then their test location. They just typed in the location box, Wells 2 PD 2017. And that gave me their results. So I can go in here and I can see, okay, Tanya and Jay, it's self-graded. Tanya and Jay struggled a little bit. Not too much, but they didn't get everything perfect. So let's see where they struggled. They got a 92%. We've got the student answers, the regular answers, and then the check as to whether they got the answer correct. So here they struggled a little bit. They did not calculate their high or midpoint or their flow direction. So that was incorrect, but then they got the rest of it. So this is nice because then you can keep track of who submits what their test is. You don't have to grade it all yourself. All right. I have gone through a lot of these slides. Here we go. Okay, going back to our full screen. In order to request a testing version, I only ask that you email us with the name of your school or your program. Because the test location sorts submissions randomly, it does tend to be best that there's one test location per class. That way you don't have to sort through everybody. So if you have a number of classes, I would give you, if you have 2 classes, I'll give you 2 test locations. If you have 1 class, just 1 test location. And then the due date that you want their project to be done by. And I would need that about 1 week in advance of the due date. So here is my favorite part, the applied knowledge scenarios. I'm going to try to run through this quickly, but I still want to give it a bunch of time. So if you have a hard cutoff at 3, Again, this will all be available to you after the fact, but this is actually really, really special because it gives students the opportunity to investigate and form an evidence-based argument to whatever they're doing, to a local project or area of concern. So the applied knowledge scenarios, we ask students to invent or to investigate a real local issue, or teachers can invent a scenario where students can then analyze research and use concepts about their community to investigate a local area of groundwater concern. So I can provide a basic applied knowledge scenario, or teachers can develop it on their own, or it can be student-led. Applied knowledge scenarios are current and timely. If you're inventing one on your own, they're locally relevant, they're related to the science content that you're learning. And they're should-we questions, they're relationship questions, they're questions that connect science to human elements. And so I'm going to quickly show an example. This is using the high-level challenge that we just did. You know, if we'd worked through it all the way and we chose wells A, B, and C, this is what our results should have been. Then I give a example, I give a situation. So here there's a small community in Nebraska that's experienced groundwater contamination from a local paper mill. And then I give an example of the contaminant, which well was released. And it's released near well E, which if I look at it here, it's released near well E. So now I take this and now I'm asking, all right, given the flow direction, which wells are going to be in danger? Which wells are going to be in danger, and how long is it going to take to travel from the source to the nearest or the furthest well that is in danger of contamination? I then get to ask a little bit more about the assumptions the Hydrogeology Challenge makes and how they might affect the real life direction. And so challenging students to think critically about the models and then make informed decisions. And then I get to ask a question about the chemical itself and whether or not it will work against, whether or not these remediation methods will work against things like chloroform, which is the chemical here. Now, I have had teachers who've had just an abundance of time and freedom, and they got to design their own curriculum, and it was so, so cool. I'm really jealous. They had their students actually go out and collect local river data and analyze it and use local maps to determine groundwater flow. So they used the Hydrogeology Challenge in order to establish those basics, and they actually calculated groundwater flow from existing maps and reaching out to the local NRD, which is the Natural Resources District. And then they investigated a potential contaminant. So what if I think it was a hog farm, or maybe it was a chicken farm. I think it was hogs. What if this hog farm is not properly managed? What if, you know, we get some gross stuff coming into our water from this particular area? Where is it going to go to? Which local cities are in danger? What's the area that, and you know, what would be the time of travel? How long would we have to clean this up? So that was just a really cool thing that I wanted to share. That. All right. Again, this is aligned to NGSS, primarily high school. And we are about out of time, so I'm going to take questions here now. But I just wanted to remind you of the various toolkits that we have. Our hands-on tools, our interactive lessons and games, our mobile applications, our learn-at-home lessons, things that can be done by themselves, things that can be done separately or with a group. And then I wanted to leave you with my contact information and then open it up to questions. So I'll put my camera back on. Hello. And if you don't have any questions now, there will be a survey after the fact. So, please feel free to write in anything there. Where did my questions box go? Not seeing it. Okay. All right. Awesome. Well, I'm not seeing any questions, but thank you again all for attending. Again, the survey and the copy of the recording from today's webinar will be emailed to you, as well as posted. Well, the recording will be posted later. And thank you again so much for joining me. I will hopefully hear from you and see you guys all again. Bye.